Hello everybody. So in this video, I will feature an application of one of the topics discussed in our class in the context of a practical application. In particular, we will discuss an application of optimal control of linear time invariant state space systems in the design of electromagnetic coils. This problem was proposed and solved in a paper by Yang et al. In the context of designing efficient controllers for magnetic micro or nanobots geared towards medical applications. We shall see that the problem can be solved by using the linear quadratic regulator optimization scheme we discussed in class. My chosen field of application is on the design of controllers for nanorobots. A well-designed nanorobot can aid in targeted drug delivery in the cellular levels, tissue-level therapies, and in minimally invasive alternatives to medical procedures. A popular way of controlling the actuations of these nanorobots is via the use of electromagnetic coil systems, or ECS. This is due to the fact that ECS can generate a dynamic real-time magnetic field that is generally harmless to live organisms. There are several ways of controlling ECS in contemporary literature, but we will focus on the control design problem described in the paper by Yang et al. In the succeeding sections, their general formulation will be discussed in the context of linear time invariant systems, and their solutions will be presented with focus on the application of the linear quadratic regulator optimization framework we discussed in class. In our reference paper, the authors considered the problem of controlling the actuation of nanorobots using electromagnetic coil systems. The idea is to drive the coils with some input voltage to create a dynamic magnetic field. They considered two types of coil driving modules, but we shall focus on one. In this approach, they considered the three-axis Helmholtz coil driven by a digital control system. The typical closed-loop system setup is described in the schematic shown in this slide. Each axis of the Helmholtz coil has three major components. First is the coil driving modules, which receive the voltage coming from some input source for probing the dynamic electric current that is passed on to the next component. The second component are the actual coils, which generate the magnetic field. The third component is a compensator, which consists of current sensors and the digital control system. The current sensors measure the generated magnetic field and provides feedback used by the digital control system for calculating the necessary control input. The control input is fed to the coil driving module as additional input, thus completing the closed loop. Okay, now we're ready to set up the system dynamics for this problem. Now the blank dynamics follow the general form as we have in class, where here x sub j represents the internal states of the system, and as the paper puts it, this doesn't have an explicit physical interpretation. U sub j is the input current, I sub j is the current on the coils, and the subscript j's represent the axis on the Helmholtz coils. Now, unfortunately, modeling the system parameters cannot be done directly. So what the authors did is to consider two sinusoidal inputs and measure the corresponding output currents, and then did a curve fitting. Now, for those three axes of the Helmholtz coils, they found the following matrices. Now, our optimality requirements would be to make the output magnetic field converge to the reference as soon as possible with a minimal additional integral action of the feedback mechanisms. In this tutorial, we will focus on the x-axis coils with the following matrices. Then for the optimal control problem, we will consider the augmented system dynamics where R of t denotes the reference tracking function, and with one additional state, little x sub j of t, representing the controller's integral action. In their derivations, the authors show that the reference tracking condition is always guaranteed whenever you have a stable system. Hence, the optimal control problem can be phrased as an LQR formulation of finding the matrix K such that the control law minimizes the cost function J for some positive semi-definite matrix Q and positive constant gamma. Since our optimality requirement is the minimization of the integral action little x of j, the original states need not be penalized. Hence, we can define the matrix Q as follows, and gamma can be any positive weighting parameter penalizing the control effort. Now we're ready to use MATLAB to solve this LTI optimization problem. The first step is to create the LTI system called sysx using this MATLAB script. First, we define the matrices A, B, C, and D from our LTI system, and the matrix Q for our cost functional. And we will call the MATLAB function SS to create the LTI system for us. After creating the system, now we will check if it is controllable. Now we can use MATLAB's CTRB command to form the controllability matrix. And we can also compute for its determinant and see that it is not zero, implying that the system is indeed controllable. Now that we know that the system is controllable, we can go ahead and solve the optimal control problem via the LQR command, which takes as inputs our matrices A, B, Q, and R, and it will output the optimal gain matrix K, the matrix P, the solution to the algebraic Riccati equation, and the closed loop poles of the system. This will tell us that the optimal gain matrix K that solves our optimal control problem is given by this matrix. Here are the references for this tutorial and some acknowledgements. That's it for now. Thank you for listening and have a good day.